Myself, Hiren Patel, Assistant Professor at LJ Institute of Engineering and Technology. So in this current video lecture series, we are studying subject of Physics Group 1. So till now, in this chapter of Properties of Matter, we have discussed the concept of stress, strain, stress-strain diagram and elasticity, elastic behavior of solids, factors affecting elasticity, and in last two videos, we have discussed the torsional pendulum. Now, in this video, we are going to study the twisting couple of cylinder or wire shaft for two different cases. So, the first case is solid cylinder and the second one is hollow cylinder. But before moving further, I would like to raise a question for you that which of the above will be suitable for industrial applications? If your answer is solid, then you are absolutely wrong. And that is the reason why we are discussing both the cases in detail. And at the end of this video, we will conclude why hollow cylinder is more suitable for various applications in industries compared to the solid cylinder. So, let's start with the first case of today's session, that is twisting couple of solid cylinder or wire shaft. So now, consider a solid cylinder of length L and radius R to be clamped at its upper end. You can see in the figure that here solid cylinder is of length L and radius R, and it is clamped at its upper end. Now, let this cylinder twisted by a couple apply to its lower end in a plane perpendicular to its length through an angle theta. So you can see in the figure that angle theta is nothing but that angle of twist of that cylinder. Now, due to elasticity of material of cylinder, a restoring couple tending to oppose the applied couple is set up in such a way that two balances each other in equilibrium position. So here we can say that here a restoring couple produced. That couple is set up in such a way that it opposes the applied couple to it. Now, here to estimate this couple, consider the cylinder consisting of a large number of hollow coaxial cylinders, one inside the other, and consider one such cylinder of radius x and thickness dx. You can see in this figure B. Here, that cylinder has a radius x and its thickness is dx. So, it is seen that radius of the base of cylinder turns to the same angle theta, but here the displacement dB dash is maximum at the rim and it gradually decreases to the zero at center O. So, here a straight line AB, you can see in the figure that here a straight line AB which was initially parallel to that axis O dash before applying a twist, that will now take up the position AB dash after the angle of twist. So here the angle of shear is equal to theta. So here, according to that figure, we can say that angle BAB dash is equal to theta. Now, it is clear from the figure B that BB dash equals to x theta, because we know that we can find that R is equals to multiplication of angle and radius. So here BB dash is the R and x is radius and theta is the angle. So we can say that from basic relation that dB dash equals to x into theta according to the figure B. Now, we know that angle of shear here phi is equals to x theta by L. So now, if the modulus of rigidity is theta, then we know that modulus of rigidity is the ratio of shear stress to shear angle. So here eta is equals to shear stress by shear, or we can say that it's angle of shear. So by subjecting that shear stress, we have the equation shear stress equals to eta into angle of shear. Now we know that angle of shear is nothing but phi is equals to x theta by L. So by replacing that value of angle of shear in that above equation, we will have the final equation of shear stress equals to eta x theta by L. Now, the shear force on the surface of hollow cylinder is stress into surface area of hollow cylinder, because we know that stress is nothing but the force per area. So here we can say that shear force is equals to stress into surface area of hollow cylinder. Now you can see in the figure B that here the radius is x and the thickness is dx. So the surface area of that hollow cylinder is given by 2 pi x dx. Now the total force on this will be shear stress into surface area. So we replace the two values. One is of shear stress and second is of surface area. Now the total force on this will be eta x theta by L into 2 pi x dx. So now the moment of force about the axis O dash of cylinder is d tau. We know that d tau is equals to force into displacement. So now we will put the equation of that total force and displacement in the equation of that moment of force. So finally we have d tau is equals to 2 pi eta theta x square dx upon L into x. So by multiplying that x square into x, we have the final equation of d tau is equals to 2 pi eta theta x cube dx upon L. So now we want to find the twisting couple. So here we can take the integration of that above equation d tau and find the twisting couple on the whole cylinder. So here the integral is taken over the two limits, that is x equals to 0 and x equals to r. So by integrating that above equation, in the limit from 0 to r, we have the next equation of moment of force or twisting couple is tau is equals to integral 0 to r d tau. Now here replacing the value of d tau, we have the next equation is integral 0 to r 2 pi eta theta x cube dx by L. Now here the variable is x. So by integrating that above equation, we have 2 pi eta theta x cube by L r is to 4 by 4. So now finally we have the equation of tau is equals to pi eta theta r is to 4 by 2L. Now we know that torsional rigidity of cylinder is nothing but twisting couple per unit twist. So now we have the final value of that twisting couple, and we know that angle of twist is nothing but the theta. So here torsional rigidity C is equals to ratio of that tau to theta. Now we have the value of tau. We replace that value of tau in that above equation and we have the final value of torsional rigidity C is equals to pi eta r raised to 4 by 2l. And this is the torsional rigidity of solid cylinder. Now, let's discuss the second case, that is hollow cylinder. So, suppose we take a hollow cylinder that has inner radius and outer radius is Ri and Ro respectively. Now, the twisting couple of cylinder is obtained as integral Ri to Ro 2 pi eta theta x cube dx upon L. Here we know that we have derived the equation of that solid cylinder. So same procedure is used here. But here we have taken the two limits Ri and Ro, where Ri stands for inner radius and Ro stands for outer radius in case of that hollow cylinder. So we have to integrate with these two limits, and we have the equation 2 pi eta theta upon 4l Ro raised to 4 minus Ri raised to 4. Now, so the twisting couple per twist for a hollow cylinder is CH equals to pi eta upon 2l Ro raised to 4 minus Ri raised to 4. So this is the value of twisting couple per twist, or we can say that torsional rigidity is CH equals to pi eta upon 2l Ro raised to 4 minus Ri raised to 4. Now, we have the two values of solid cylinder and hollow cylinder. Now, considering the material of two cylinders having same density, same length and same mass, and now we will take the ratio to CH and CS. So here that ratio CH by CS equals to, we have replacing the values of CH and CS in that above equation. So finally we have CH by CH equals to pi eta upon 12 R raised to 4 minus Ri raised to 4 upon pi eta upon 12 R raised to 4. So by neglecting that common term pi eta upon 12, we have CH by CS equals to R raised to 4 minus Ri raised to 4 upon R raised to 4. Now, we know the basic formula that we have used is R raised to 4 minus Ri raised to 4 is equals to Ro square plus Ri square into Ro square minus Ri square. So, by replacing that value here, finally we have that ratio CH by CS equals to R square plus Ri square into Ro square minus Ri square upon R raised to 4. The mass M is given by pi bracket Ro square minus Ri square into L into rho. Here we have used that basic formula, that is mass equals to density into volume. Here density is rho, and the other term pi Ro square minus Ri square into L is nothing but the volume of the cylinder. So according to that basic equation, mass equals to density into volume, we have the final equation of mass M is equals to pi Ro square minus Ri square into L into rho. But here we have considered the same length, so we can replace that Ro square minus Ri square with R square. So now we have final equation of CH by CH equals to Ro square plus Ri square upon R square. Because here we have replaced that value of Ro square minus Ri square into R square in above equation. So finally we have CH by CS equals to Ro square plus Ri square upon R square. Now here Ro square minus Ri square equal to R square gives us that Ro square plus Ri square greater than R square. So from that relation, we can say that CH is always greater than CS. So, what we have concluded that CH stands for twisting couple for hollow cylinder and CS stands for twisting couple of solid cylinder. So, we have concluded that CH greater than CS. It means that twisting couple on a hollow cylinder is greater than the twisting couple on a solid cylinder having same material and same length. So this is about the twisting couple of solid cylinder and hollow cylinder. We have derived the value of both the couple and we also compare that two couple, and finally after the derivation we have concluded that twisting couple of hollow cylinder is greater than the twisting couple of solid cylinder. But here the condition is that cylinder has same material and same length. So this is the reason why hollow shafts are preferred over solid shafts in rotating machinery. So that's it for today's session. Now in next video we will learn about the cantilever in different cases. So that's it for today's session. Thanks for watching.